Measurement uncertainty, accuracy, and precision. Counting is the only type of measurement that is free from uncertainty. So if you have a bunch of pennies in your pocket, you can pull them out and count the pennies, and you can say that you have exactly 12 pennies in your pocket. So the result of a counting measurement is an example of an exact number. The numbers for defined quantities are also exact. So when we say that 1 foot is by definition is defined as 12 inches, then 1 foot equals exactly 12 inches. And the same for all of these other measurements. We can define one quantity in terms of another quantity, and then those numbers inside of that quantity are exact. But beyond that, every other time that we try to take a measurement, there's some amount of uncertainty involved. So when you place an object on a balance, for example, and you get the mass of the object, even when you're weighing yourself at home, maybe you have one of those balances that has a needle, and you stand on the scale and the needle kind of sits between two numbers. You kind of have to guess where that number, where the needle sits. Is it on a 37, or is it on a 38, or is it 37.5? There's some amount of uncertainty in that measurement. One, due to your inability to see exactly what you're looking at, but two, because the nature of measurements is that there's always some small amount of uncertainty in every measurement, because measurements are not exact numbers. So one of the ways that we deal with uncertainty is that when we're trying to report a measurement, the results of a measurement, I always have to determine how many significant figures there are, how many digits I'm allowed to keep in that measurement. So, for example, here's an example that's like the one that I was discussing with the scale, where the number kind of sits, the measurement sits between two numbers, two markings on the scale, and we kind of have to make an educated guess as to where that number is. So in this one, if we look over here on the biggest scale, it looks like the markings are supposed to indicate 1 milliliter. So this goes 20, 21, 22, 23, 24, 25, right? And there's 20 down here and 25 up here. So each marking is supposed to indicate 1 mil. So when we go a little bit closer, we can see that it's about 21, and this is kind of, we always want to measure from the lowest part of this curve, the lowest part of the meniscus. So here at this scale, it looks like it's maybe about halfway through, maybe 21, and then halfway between 1 and 2, so maybe 21.5. But then if I zoom in a little bit closer and I look here, then it looks like here's 20, here's 21, here's 22. So it's not quite 22, but it looks actually like it's a little bit higher than halfway. So maybe I'd say this is 21.6 milliliters, and I could make that guess, and I could say that it looks to me like about 0.6. So what that means is that last digit in my reading, 21.6, that last digit is uncertain. 21.6 milliliters. So this number right here is uncertain. Could be a 6, but it looked like it was a 5 over here, so it's kind of a guess. And so there's a little bit of uncertainty in that measurement. Okay, so again, in this measurement, the 2 and the 1, 21.6, those are certain because I can look at there and say it's not 20, and it's even higher than 21. I can see those markings, but it's not quite 22. So I'm making a guess at that one in between 21 and 22. So 2 and 1 are certain, and 6 is an estimate. So what that means is that if there's some amount of uncertainty in a measurement, then I have to have a way of capturing how certain a measurement is, because some measurements are better than others. And so the way that I can determine or represent that one measurement is better than another is by determining how many significant figures or significant digits there are in a measurement. And a significant figure is really just a digit that's important in that measurement. So every number that's not 0 is always significant, and sometimes 0 is significant. So in general, we say the more digits a measurement has, the better it is. If you're trying to measure the mass of one hydrogen atom, and you find with one balance that it weighs 1.01 atomic mass units, and with a different balance you find that it weighs 1.011, and you get that extra digit, then that's a better reading, that's a better measurement, because it has more digits. And the digit that's not the last digit has become a certain digit rather than an uncertain digit, rather than an estimate. So numbers that are always significant are those that are not 0. So really the only time that we have to determine whether a number is significant or not, that we have to ask ourselves if it's significant or not, is if it's a 0. Because if it's not a 0, it's always significant. And sometimes zeros are significant and sometimes they're not. So we have to look at the different kinds of zeros there are to determine if the ones that we're looking at are significant. So let's look at a couple of examples here. This number here, 3090. There's no decimal point, so this number is kind of left up to interpretation. But because there's no decimal point, generally we would assume that the decimal point is over here after the last digit. So then I would read this number as 3090 is what it looks like. But really, without having a comma or a decimal point, it's kind of ambiguous what this number is. Either way, if I interpret this as 3090, then this is the thousands place, hundreds place, tens place, and the ones place. So there are two kinds of zeros in this number. This 0 here is in between two numbers. So sometimes we might call that a captive 0, or sometimes we might call it a sandwich 0 or an interior 0. It's a 0 that is sandwiched in between two numbers that are not 0. So this kind of 0, this captive 0 or interior 0, is always significant. These are, when they're in between two numbers that are also significant, then they themselves must be significant too. This 0 here is called a trailing 0. This is a 0 that comes after all the numbers that are not 0. So if all of the numbers that are at the end of a number are 0, then they're all trailing zeros. They come at the end. Trailing zeros might be significant and they might not be. So there are two examples. Here's an example of a trailing 0 where there is no decimal point. This trailing 0 is not significant because there is no decimal point here. When I look at this 0 over here, this is the same kind of number. It goes non-zero, 0, non-zero, 0. Just like this one, non-zero, 0, non-zero, 0. So this captive, the interior 0, is always significant. It's significant here. It's between the two numbers that are not 0, and it's significant here. It's between the two numbers that are not 0. But here, this trailing 0 is not significant here because there is no decimal point. And in this number here, the trailing 0 is significant because I have a decimal point here. And so what that means is that if I have a decimal point and I have a trailing 0, then it becomes significant at that point. The other kind of 0 is a leading 0, and these leading zeros are out in front of a number, 0.00, for example. Whenever a number is smaller than 1, it's going to have a 0 in the ones place. 0 point something. Whenever a number is smaller than 1 like that, then it's always going to have at least one leading zero, but often it will have more leading zeros. This number is smaller than 1, and it has 3 leading zeros. 3 zeros that we have before we get to the first number that's not 0. So in general, we say any 0 that comes before the first non-zero number is not significant. So this number here starts with zeros, 0.008020. These first 3 zeros are not significant because they come before the first non-zero number. Over here, the first number is a not zero number, so it doesn't apply. There are no leading zeros when a number is bigger than 1. It only applies when the number is smaller than 1. When we are multiplying and dividing and adding and subtracting numbers, some that might have decimal places and some that might not, it's important for us to consider how many digits we're allowed to keep in the result of those calculations. So when I add or subtract two numbers together, or multiply or divide two numbers together in a calculator, sometimes I'm left with lots of digits. Sometimes the calculator might give me 12 different digits from the result of that calculation. But according to precision and in scientific calculations and scientific measurements, it's important that we only keep the numbers that have physical meaning, that we're allowed to keep based on the rules of significant figures. So when we add or subtract numbers, we can only keep the number of decimal places in our answer as the number with the fewest amount of decimal places that we're adding together from the question. So if I add two numbers together, my answer can only be as precise as the least precise number of those that I'm adding together. And the same is true when I multiply and divide. If I multiply two numbers together, my answer has to have the same number of significant figures as the number with the fewest significant figures of those that I was multiplying together. So then, of course, we have to round. If we are supposed to lose some digits based on our significant figure rules, then we have to either round up or round down. And if a number is less than 5, we round down. And if it's 5 or up, we round up. Okay, so here's some examples of this. If I'm allowed to keep 3 significant figures, then my number here, remember these first two zeros are not significant, so I have 5 significant figures here. So in this case, if I'm allowed to keep 3, I'm allowed to keep 2, 8, 6. So that means that I would look at this number here, the 7, and this, when I look at this 7, this number is going to tell me whether I'm supposed to round up or down. So a 7 is bigger than 5, so then I would round up. So 0.286 is going to round up to 0.287. So let's look at this one. I'm supposed to keep 3 significant figures here, so I keep the first 3, 1, 8.3, and then I look at the digit immediately after that, this 3, and if this 3 is 5 or up, I round up, and if it's 4 or lower, I round down. So this is 3, so I round down. So 18.3384 rounds down to 18.3. 6.87, if I keep the first 3 significant figures, I'm allowed, according to my rules here, I'm allowed to keep 3 significant figures. Then 6.87, I would look at the number immediately after that third significant figure, and if it's 5 or up, then I'm going to round up. So in this case, 6.87 is going to round up to 6.88. And finally, 92.85, I would look at the first three numbers, 92.8, and I'm going to look at this 5. And there are conflicting rules about how you should round in this case. Generally, my rule is that if it's a 5, it's going to round up. But according to this text, 5 rounds up when the retained digit is even. And 5 and when, so we're going to round up or down depending on whether the retained digit is even according to this rule. So here, if I rounded up, I'd get 92.9, and my retained digit would be odd, and that would be against this rule. So instead, I'm going to round down. 92.85 is going to round down to 92.8, and again, my retained digit is even in that case. So the difference between accuracy and precision is illustrated pretty well by these three pictures here. So precision is when I'm doing target practice and all of my shots are grouped together really tightly. So here is an example of 3 shots that were very precise, but they weren't particularly accurate because they weren't in the middle of the target. So maybe the sight on my gun was not calibrated properly. So I was aiming at the middle every time, but the gun was ending up over here every time. So this is precise, but not accurate. Here, these shots are not in the middle, and they're not even particularly well grouped. So maybe I'd have another shot over here or something. And when shots are not particularly well grouped or in the middle, then we'd say that they're not accurate or precise. And here, in this case, they're all grouped together very tightly, so they're all very precise, and they're in the middle of the target, so they're all very accurate. So the idea here, how this applies to scientific measurements, is that when I'm performing a measurement, if I get the same measurement, the same value every time I make that measurement, then my measurements are very precise. But maybe I'm getting the wrong value. So maybe I'm weighing something that weighs 5 grams, and every time I put that object on the balance, it says 5 grams, but that object actually weighs 4 grams. So that would be just like this, this example here. I'm always getting the same result, 5 grams, but it's not the right result. So maybe there's something wrong with my balance in that case. And if I weigh an object and one time it weighs 5 grams and one time it weighs 7 grams and one time it weighs 4 grams, then and it actually weighs 3 grams, then those measurements are not particularly valuable at all. None of them are close to the middle, and if it's not repeatable, if you're trying to take measurements and every time you take a measurement you get a different value, then there's something wrong with the way that you're taking that measurement, or there's something wrong with the device that you're using to take that measurement. And those measurements are not going to be of much use. So here's some real data. We can look at some actual numbers here and determine whether these are accurate or precise. So 10 ounces is 296 milliliters. So we're trying to determine whether these dispensers, the cough medicine dispensers, are accurate. So let's look at this one. These numbers are pretty close together, 4.1, 3.9, 4.0, 4.1. This one's kind of far off, but maybe it's an outlier. These ones are all grouped together pretty well. So I would say that these numbers we're getting the same number. These are precise numbers, but they're not right because it's supposed to be 296 mils. So this one's about 12 mils short. So it's precise but not accurate. These numbers over here, 298 to 294, 296, 297, 293, these are jumping all over the place. So they're closer to the value of 296, but they're not precise at all because they're jumping all over. So these are not this measurement is not repeated very well. Maybe the way that I'm doing the measurement is not the same every time. And here, these numbers are very closely grouped together. 296.1 appears 3 times. So it's very precise, and they're really close to the actual value, so they're also very accurate. So dispenser number 3 is both precise and accurate.